hydraulic systems, flow is created by pumps. The flow of hydraulic fluid causes actuators to move. Thus, flow created by a pump is responsible for motion in a hydraulic system. Flow may be measured as the velocity of the hydraulic fluid through the conveyors in a system. Velocity is defined as the average distance traveled by the fluid particles per unit time. It is normally measured in feet per second, or FPS, through conveyors. The flow of hydraulic fluids can also be measured by their flow rate. Flow rate is defined as the volume of fluid passing a point per unit time. Large flow rates are measured in gallons per minute, or GPM, while smaller values are expressed in cubic inches per minute. These rates are used to calculate actuator speeds. The two units of flow rate measurement can be easily converted to each other. In the given example, the distance between point A and point B is 2 feet. As the fluid moves from point A to point B in 1 minute, the velocity is 2 feet per minute. Also, 1 gallon of fluid passes through point A in 1 minute. Hence, the flow rate is 1 gallon per minute. Note that the flow rate of the fluid is fixed. The velocity may still change due to the change in the diameter of the pipe. In this example, the velocity of fluid between point B and point C is 1 foot per minute, at a constant flow rate of 1 gallon per minute. When a fluid flows through a constant diameter pipe, the pressure at any point downstream is always lower than any other point upstream. This is so because there is pressure drop as the fluid overcomes the friction in the pipe in order to flow. This is similar to the example of different resistances arranged in series in a circuit. Here, the pressure is maximum at the start of the pipe because the friction that must be overcome is maximum at this stage. Similarly, the pressure at the end of the pipe is minimum as the friction to be overcome is minimum. The figure here illustrates the principle of pressure drop due to friction. The succeeding pressure drops are shown as decreasing heads in succeeding pipes. In the previous example, fluid level in successive vertical points was different because of the pressure differences at these points. Note that, in the absence of pressure, whatever the shape of the container, fluids seek the same level. When pressure is applied at one point, the levels at the other points rise. The levels at these points rise so that the weight of the fluid column balances the additional pressure. The extra pressure is required to overcome the weight of the fluid column. Thus, hydraulic circuit design must keep in mind the workload or pressure to overcome the weight of the fluid, in addition to pipe friction and fittings, as well as the load on the actuator. When fluids move through straight pipes, the fluid particles move in parallel flow paths. This condition of flow is called laminar flow. It is easier to maintain laminar flow conditions at lower velocities of fluid flow. Frictional resistance to flow in the pipe is minimum with laminar flow. When fluid flows in such a manner that fluid particles don't move in a straight line or parallel to the flow direction, then this flow condition is called turbulent flow. Turbulent flow can be caused by high flow velocities or by abrupt changes in the direction or cross-section of the pipe. Turbulence leads to increased friction in the pipe, increasing operating pressure, and waste of power in the form of heat generation. In a working hydraulic system, a hydraulic fluid contains two forms of energy, kinetic energy and potential energy. The kinetic energy is represented by the velocity and weight of the fluid, and the potential energy is in the form of pressure created by the resistance to flow. Daniel Bernoulli, a Swiss scientist, proved that, at a constant flow rate, the total energy in a hydraulic system is constant. If one form of energy is reduced, it must be transformed to the other form of energy. Here's an illustration of Bernoulli's principle. In this system, fluid is flowing in a pipe of varying cross-sectional area. In regions where the cross-sectional area is greater, the fluid's velocity decreases. As a result, the kinetic energy of the fluid is reduced. This results in an increase in the potential energy, as stated by Bernoulli's principle. This fact is indicated by the increase in pressure in this area. Similarly, a decrease in cross-sectional area leads to an increase in kinetic energy and a decrease in potential energy or pressure. In both cases, it's important to note that the sum of the two energies remains constant. In an automobile engine, a carburetor barrel uses a venturi, or narrow throat, to reduce pressure during airflow. As air flows through the barrel, its velocity increases as it passes through the venturi. This increases the kinetic energy and reduces the pressure energy. Due to this decrease in pressure in the venturi, gasoline gets pushed inside and is vaporized and mixed with the airflow. Let's see how friction and velocity affect pressure. Due to reduced friction, pressure in the system is reduced at successive points downstream. The only exception is at points where the cross-sectional area increases. Here, the increase in pressure is due to a decrease in velocity. When designing spool-type hydraulics valves, it is important to keep Bernoulli's principle in mind. Here, changes in fluid velocity are common, and if the flow rate is allowed to go beyond the maximum rated value, unbalanced axial forces arise within the valve and it malfunctions.